Okay, hi.
Well, live. One sec. Yeah.
Okay, hi everyone. Mm, My name is Isaac Omoruyi. I'm a software engineer at Moniepoint, and in today's conference, I'll be speaking on massive scaling of transaction processing with Kafka. Right? Okay. So yeah, for things I'll be talking about, first of all, I'll be starting off with the background of the products that we set out to build, what we intended on doing, what we try to achieve. Then I'll also be talking about secondly, I'm talking about the initial approach we took. That's the initial product, how we built the product initially. Then I'll also be talking about the drawbacks we experienced with that particular product or that particular implementation of the product. Then next up, I'm talking about the alternative options that we considered when we wanted to switch away from the initial approach that we took. Then I would also be talking about as our why we ended up choosing Kafka as the approach we wanted to use to implement this new system that I wanted to build. Yeah. Then basically I'm talking about how we implemented Kafka as a solution into the system that we're trying to build. Yeah. So to start off, background. So yeah, at Money Point, we were trying to build a generic internal system to process transactions. When I'm talking about transactions here, I'm talking about transactions like settlements, reversals, or some transactions that required some form of query or something. We needed this to be able to scale and to be able to process millions of transactions per day. Because obviously we're a growing company, and over time we need to process a lot more transactions. And initially we built a system to do this, right? So next up is the initial approach that we took. So for the initial approach that we took in while building this system, we went with an approach of so we needed some form of okay. Let me explain the product first. We needed something that was sort of going to act like a queuing system, right? A generic system that allows people to a generic system that allowed various services to take care of their own business logic and kind of write to a particular queue, right? And this service that we're building is going to take care of these transactions that have been sent to the queue. Go ahead and try to process the transactions based off the parameters or the information that has been sent for those particular transactions. Handle things like check whether the transaction is successful, whether the transaction should be retried over time, whether the transaction is invalid, whether it's expired, or just a lot basically. So there's a lot of things that go on with these transactions that we're trying to process. And we get the generic system that various systems or various services could talk to, just like send these transactions to this particular system or to this queue that this system is going to read from. And the systems, those other systems that the services that send these transactions can just go ahead and process their own, like do their own various business logic without having to bother about these transactions they've sent, right? So yeah, that's it. So the initial system we built was making use of DB. So we took a DB approach, right? Using a DB as a form of a queuing system. So we wanted to queue these transactions that were to be processed in the DB, right? Then after while queuing these transactions in the DB, so to start with, these transactions have the format of the transaction is stuff like it takes in the attempt count. That's the one that has been sent into the queuing system. So a transaction or like a transaction blueprint can be something like the reference of that particular transaction, the callback URL, that's where the transaction is meant to be called so that it can get processed by a particular service. The attempt count, so last attempt date time, just a lot of metadata basically for that particular transaction, the status of the transaction, and yes, a lot of other things and some other things. So this system that we built that makes use of a DB and some form of scheduler that is going to be processing, like running at intervals to process these transactions. It was making use of a DB initially, right? So we send these initial transactions that we process into this DB in form like to act like a queuing system. So that's this guy here, this service one, service two, service three. They all send transactions. This is the database here. They all send transactions into this table in this database. Let's call the table new transactions, right? So they send all these transactions here. Then we have this our service that we build. Let's call it transaction processing service. So this guy reads these transactions from here. So it has this guy has like three different jobs running at the same time. The first job is the guy that just goes ahead and reads the transactions from this particular table, right? When you reads these transactions, so these are transactions that are to be processed. It goes ahead and if it's a transaction from this guy, then it saves these transactions like in batch. Say we have want to be able to process 6,000 at a time. It saves this transaction into this particular table, which is the processing transaction. Then we have a separate job that reads from this processing transaction and tries to process those those transactions that we process. We then go ahead and process the transaction in a way that we call. So, like I said, there's like a callback URL that this transaction is that we're going to use to process transactions. So this system goes ahead and calls that particular URL, right? Gets the transaction processed in some form. We get a new status for that particular transaction. So it's possible that the transaction that was sent could have a status of maybe successful, it could have failed, it could be invalid, or it's still pending. So based off that, we modify this guy in the DB, the status of this particular transaction is in DB. Then there's a third job that goes ahead and just reads from this particular processing transactions, and the guys that are either successful or maybe expired, we go ahead and save them into the archive transactions table. um Recall that I said that we do this in a batch size, right? So these guys that are saved into the processing transactions are saved in batches. So let's say we need these processing transactions to be able to only contain like 6,000 transactions at a time, because we're trying to implement rate limiting to prevent things like DDoS and all that stuff. So that's how this guy was initially working. And yeah, this worked well for a while, but then we're trying to scale, we're experiencing some issues. So that's when I go to the drawbacks that we're experiencing with this particular implementation. Yeah. So for drawbacks that we're experiencing, we, like I said, we're doing rate limiting, and because we're doing rate limiting, we had to pick a particular batch at a time, which could lead to maybe increased processing time, and some other things. Then since we're also using like a traditional relational database management system, we're also having things like it lacks a distributed feature in the sense that we could not really scale horizontally. So if we have millions of transactions, we could be experiencing issues at that point in time because we can't scale horizontally. Then also typical with database, right? Things like database locks. And the reason that this is like a drawback is because we could have various jobs trying to read or write to a particular row in the DB for a particular transaction, and this could like lead to more wait time, and yeah, just generally leading to increased processing time. So we wanted to like stop all of this or prevent all of this, and wanted to look for a better way or better alternatives to this system that we're trying to design. So that's when we tried to think about various approaches that we could take, and we wanted to go with a queuing system or systems that could act in form of streaming platforms or like queues and all that. So we had three options in mind. The first one was Apache Kafka, second was RabbitMQ, and the third was KubeMQ. So with RabbitMQ, obviously we went to Apache Kafka, but with RabbitMQ, we didn't go with RabbitMQ because of some certain things. So it's not good for event streaming. One, it's not it doesn't have retention in the sense that data doesn't get retained. So once the consumer reads that particular data or reads the particular message from a certain queue, the message is gone. It doesn't stay in the queue. And overall, yeah, it's it's not a better system for what we wanted to achieve than Kafka. And second one was also KubeMQ. So KubeMQ seemed to be a good option, but the only issues we had with this KubeMQ was the fact that it wasn't a mature product back then, or when we initially doing this, it wasn't a mature product, and we did not have like any, should I say, like production experience with this KubeMQ, but we had with Apache Kafka. So then we decided to go with Apache Kafka. Um, so next up is why we chose Apache Kafka. So number one, we chose Apache Kafka because it's a distributed system. When I say distributed system, I mean that it's a system that allows us to scale horizontally very well. So we can have different servers for the same different servers with different Kafka brokers, allowing us to scale. So it's just about creating new nodes and different servers, allowing us to scale. So no matter the number of transactions we have, we can just keep on having extra servers and all that. Number one, then it's highly efficient for data streaming. So like real-time data streaming, if you want like real-time data, it's very good for that. It's very fast. So it has very high throughput. So it allows for processing of multiple transactions or whatever you want to process at a time. Then also it has data retention capabilities. Having data retention capability means that even if we've sort of consumed these messages from from the particular topics, we still have access to them at some, like, any whenever we need them. So if for some reason we are experiencing, or there was a problem when we initially read these messages from the Kafka topic, we can go back and just reset or change the consumer group name, and we can start processing these transactions again without any problem, because we still have access to these transactions. Then so yes, these are the things that Apache Kafka provided for us, and yeah, it's met our needs and requirements. So we went with Apache Kafka. Now, implementing Apache Kafka as a solution. So in trying to implement this Kafka, in trying to implement Kafka as a solution into this product, as the let me call it the transaction job service that we're trying to run, we did this. So this is like a flowchart of how the current system works, right? So the way Kafka works is you have the Kafka server at the center of it all, or that can contain several brokers with topics and partitions and all that. So you now have a producer that sends or produces messages. In Kafka, it's called messages. It produces messages to this to these topics in the Kafka server. Then you have a consumer somewhere else, maybe under service or something, that subscribes to these topics in the Kafka server and acts on these messages in whatever way they're meant to do act. So yes, we have, looking at this, we have producer one, producer two, producer three, and producer four. We can think of this as various services. Let's call this maybe a settlement service. Let's call this recurring service, let's say deposit service, or reversal service. So this guy send, or they produce, we sorry, they produce to the Kafka server. And in Kafka server, we have a topic that these guys produce. So we call it the attempt topic. The attempt topic is the guy that holds the transactions that we process initially. So when we just initially get transactions fresh, they are sent to this attempt topic. So all of them here, all these guys all sent to the attempt topic. If you can see in the Kafka server, we have three topics there. We have the attempt topic, we have the retry topic, and we have the archive topic. So these producers that have transactions that we process, they all produce the attempt topic. Now, for this attempt topic, and for all these topics, we have various instances of this transaction service that are subscribing to these topics and like trying to do some form of manipulation on all that. So for the attempt topic, we have the attempt service. Let me call it the attempt service that's subscribing to the attempt topic. For the retry topic, we have the retry service that subscribes to the retry topic. For the archive topic, we have the archive service that subscribes to the archive topic. Now, let me just go straight up to the archive topic. So what the archive topic does is, what the archive service does is rather what the archive service does is it consumes message, subscribes to the archive topic and consumes messages from it, and all it does is really just save it to a database. I'll talk about database later. Then so that's it for the archive topic. It's just straight, like there's no form of extra manipulation of that. It just gets the messages and saves them into the archive um, archive table in the database. Now back to the attempt topic. So what the attempt topic does is it consumes from this particular, sorry, what the attempt service does is it consumes from the attempt topic, right? Then it it makes a call to the URL that has been provided for that particular transaction. When it makes the call, it could be that that particular transaction is not meant to be processed at that point in time. So sometimes some people want to, some particular service may say they want to delete their transaction. They don't want to try it now. They want to try it at a later time. So for those guys, what we do is we send those guys to the retry topic. So we produce from this attempt service into this retry topic here. That's what happens here. But for the ones that want to be processed at that point in time, we'll go ahead and try and process them. We call the service that is to process them, and we get a status after processing. So we could get maybe a successful status, we get an invalid status, maybe pending requery, um, um, expired, or all that. So based off what we get, we know what to do with that particular transaction. So when it's successful, it means that we're done with that particular transaction. It's done processing. So we just go ahead and produce it to the archive topic, and we have the archive service that can in turn consume that particular message that has been produced to the archive topic and sent to the archive transactions table. Then say we have same thing for invalid. So invalid transactions go here and get sent to the archive transactions table. But say we have things like pending requery as a as a status for that particular transaction. if a transaction is pending inquiry, that means it's meant to be retried at a later time. And this attempt guy, since we've separated consents, all it does is it just posts the transaction, so it sends it to the particular job URL to process, right? So since this transaction that has been processed is pending inquiry, we'll go ahead and send it, we produce it into the retry topic, where the retry service is meant to act on this retry topic. So that's it really for the attempt service. Then for the retry service, what the retry service does is it's it's subscribes to the retry topic, then it checks whether this particular it checks whether this particular transaction is ready for retry, because we have like a retry interval in the job in the transaction, rather that's the transaction um, in the transaction. So it checks whether this particular transaction is to be processed, whether it's ready to be retried. If it's not ready to be retried, what we used to do back then was we used to just send it back to the retry topic. So it's possible that you can have the same message coming over and over, not ready for retry. Say it's meant to be retried every in the next 5 minutes. So it comes now, it's not ready for retry. Send it back to the retry topic, and it goes on and on until it's ready to be retried. So for the transactions that, so that's how it was back then. So for the transactions that can or are to be retried at that point in time, we go ahead and call them, like call the service to get the new status of that transaction. Then based off that, if we have like a successful response, same thing that happens with the attempts there, we send it to the archive topic so that the archive service can pick it up and archive it in the archive transactions table. So if it's not ready for retry, we'll go ahead and send it back to that retry topic. If after trying to retry it, we get a status of maybe failed or some other status, we can go ahead and send it back to the attempt topic to actually get attempted again. So that's how it works. Now, the issue with this retry service and how it was working before was that for jobs that are not ready for retry, we keep on sending them back to the retry topic over and over and over again. And because of this, we had like very high data rates being produced to this guy, and because of that, it's obviously going to be incurring more cost. So in order to prevent this, what we did was we needed to make use of a DB that can scale very well, right? So we need to make use of a DB that can scale very well. And what we do is we check this guy, and if it is not ready for retry, we go ahead and save it in this data in this table in database. The database we're using here is Google Spanner. That's Google Spanner's database. It's very good to for it's also like a distributed system, because you can have various servers for the spanner, and it allows you to scale very well horizontally, allows you to be able to read and write read and write to the DB or from the DB like a lot. You can see maybe 100,000 100,000 queries a second. So Spanner allows you to do all that. So it was very good for scaling. So you have a lot of transactions. So Spanner was very good for that. So yeah, we send these guys to the Spanner to this Spanner DB. That's the retry transactions table in the Spanner DB. Now, for this retry transactions table in the Spanner DB, when we're trying to save these transactions, the intention at the end is to have a job, like let's say a Kubernetes cron job, that picks picks jobs that are now ready for processing. Let's say the job runs every 1 minute or every 2 minutes. It's going to pick jobs that are ready for processing and go ahead and send them back to the retry topic so they can be picked up by the retry service and retried at that point in time. But we also needed this to scale in the sense that we don't want to just have one job, because typically if you're making use of jobs, you want maybe you don't want to have multiple instances of that job, because if you're having multiple instances of that job, you can have multiple jobs picking up the same entry and acting on that entry. So we did not want that. We don't want that issue, and we also needed to ensure that we could scale and have multiple jobs running at a time. And to achieve this, what we did was we used a concept from consistent hashing. I'll get back to there. So we use the concept from consistent hashing, where we get the hash value for a particular transaction, right? And when we're saving it in the DB, we save it to that particular hash value, so that we can have various jobs. So if you look at this diagram here, you can see we have cron job 1, cron job 2, and cron job 3. You can see that cron job 3 is taking 0 to 120. So anything that falls between 0 to 120, when it gets saved into the DB, is going to be picked up by this particular cron job. Anyone that has a value between 120 and, let me say, sorry, 0 to 119, 120 to, let's say, 240, and 241 to 359 and 360. Right? So if you look at this transaction now, this guy was stored on point 60. So because it was stored on point 60, we can have multiple jobs running, and the job that is going to get to pick this guy up is going to be this cron job 3. Same thing with this transaction 2 and transaction 3 here. They get picked up by cron job 1. And same thing with this transaction 4 and transaction 5. They get picked up by cron job 2, right? So now we can say that we don't want to even have just 3 instances of this cron job. We can say we want to have 10 instances of this cron job. All we have to do is just shift the way that these cron jobs have been allocated to this particular circle, right? So we can say we want to have 5 cron jobs now. So we'll just change this one to maybe 0 to 90 and all that. And as a result of that, we can have multiple jobs running at the same time and picking up these transactions and we'll not have the issue of multiple jobs picking up the same transaction over and over, multiple jobs picking up the same transactions. Yeah. So to compute this particular hash value, what we use is this formula. That is, to get the hash value, we just get the hash code of that particular transaction, say of the reference or something. Then we get the hash code modulo of the hash upper bound. So this hash upper bound in our case in this circle is going to be 360. So it's possible that your hash upper bound could be different. It could be like 720, it could be 1200. So if it's 720, that means you're going to have various jobs that are shared between 0 and 720, while your transactions also get spread between 0 and 720. So it's the same concept of like modulo where you get the remainder. So that's what this guy is for here. So yeah, so that's how this guy works, and that's how we're able to ensure that we could scale here, like have multiple cron jobs running without ever bothering about this multiple jobs picking up the same transaction. So back to this, when we try to save in the retry transactions table from the retry service, we compute the hash value for that particular transaction and save it into the DB. So when the jobs that are running are trying to pick up from this retry transactions table, for the guys that are ready for retry, we also check that particular hash value and ensure that that job is meant to pick up from that particular hash value range. So that's how we're able to achieve this. So yes, so we pick up from this guy, the job picks up from this guy, sends it back to the retry topic. Then the retry service can now go ahead and consume those jobs that are now ready for processing from the retry topic and process them. And based on the status that we get after processing, we can either send it to the attend topic to the archive topic to be archived, or maybe to the attend topic. So yeah, this is how we're able to build a system that is able to scale at large to be able to process, say, for a particular product that we have, we use this guy to process like 40 million transactions a day. And for other products, we have like how much they're also processing a day. So we've been able to use Kafka to actually like scale at large, and it's been very, very helpful. Now, okay, I don't think I had this as part of my slides, but I think maybe some disadvantages we've had, if any, are so Kafka is like, so should I say, it's expensive to operate, and especially if you are doing it yourself. So initially, when we started, we were trying to use Streamzy, right? And it was a nightmare because there was a lot of things involved, and we didn't want to like allocate so much resource into trying to optimize and do all that stuff. So we just went with a managed version of Kafka. We were currently using Confluent, right? So it's Confluent basically handles all these things for us. We don't need to bother about ensuring that the configurations for our Kafka servers are good and all that stuff. Confluent just takes care of that for us. Then any other maybe another disadvantage, I don't want things more of a disadvantage, probably maybe not a disadvantage really. It's not a disadvantage actually. So I think I would like to, it's really, really fast. So there was an issue that we experienced where we're trying to debug something for a while, and the reason why like the system was misbehaving was actually because the Kafka guys, or the services, the Kafka guys were producing too quickly, and the consumer guys were consuming too quickly. And because of that, the service, or the way the system was, the design was like flawed because of that. So after realizing that, after a while, we had to change the approach of the system. So yeah, I think that's really it, how we've been able to use Kafka to scale our transaction processing. Yeah, thank you very much for listening. And yes, you can reach us at Moniepoint on the support at moniepoint.com. We're here trying to power the dreams of businesses and their customers in emerging markets. Thank you very much for having me. That's it.
All right. Thank you, Isaac. We have a bunch of questions from the chat, and I think we have about we have a few minutes actually to answer questions. So I'll just go through them. So someone said, I know that transaction processing is mostly a request response type of operation. How do you process and return responses in the same request response cycle as Kafka does asynchronous processing? Or do you return an initial response if the transaction is acceptable and then do continuous query till the transaction is in the final state? So the question here is, how do you ensure request responses in the same cycle? Sorry, how do you ensure you get responses in the same request response cycle from Kafka? Like, do you do like polling to get like the response later, or do you have like a mechanism to make sure you get response from Kafka now?
Oh, so Kafka is not the guy that is processing transactions. We're just using Kafka to store these transactions that are to be processed. We have a separate service that does the actual process of transactions, right? What happens is this service subscribes to a topic and gets these messages or these transactions that are to be processed, goes ahead and processes them. So it's not Kafka that does the processing of the transactions. It's the service that does the processing of the transaction. What we're using Kafka for here is to ensure that we're able to send this data very, very quickly, and like we're not having anything like delay or lock issues or scaling issues or delayed processing. And yeah, I don't know. Does that answer the question?
Yeah. Thank you. So let us know in the question if Emmanuel, let us know in the Q&A section if like you have your answer. The next question is, and I think you answered this. Did you face any challenges with managing Kafka clusters?
Yeah, we definitely did.
So
It was
what
actually
were the challenges?
Challenges. We how do I explain it? It was just a nightmare, really, in the sense that it was not properly scaling for us. We maybe downtimes and all that. So we just needed someone that or an external provider that actually provides like manage Kafka for us. We don't have to bother about trying to fine tune the Kafka, like ensure that it's working for us very, very well. So it's similar to something like RabbitMQ where you have I don't know if you know Winnie Mustang or something. So it's all these managed platforms where you can just all you need to bother about is just send your own transactions to that particular queue that they've designed for you, to the
Yeah.
particular server that they've designed for you, and like consume from it. So you don't have to reinvent the wheel, really. That's just it. So we
So
found something that it
the
was.
Kafka you needed for scaling needed to be scaled first. You needed to.
I guess. I
Yeah.
mean, yeah, I guess you can say that too.
All
Yeah,
right, cool. Thank you. Yeah, that's fine. Then someone asks, is there a situation where multiple transactions have the same hash value?
yeah. You are going to have multiple transactions having the same hash value. Like definitely, the idea is not, or the idea is not, or having these transactions having various transactions having multiple having the same hash value is not a problem at all. What matters is the fact that they are kept in this point in that, okay, let me use the circle. They are kept in this particular point in that circle, and there's a specific job that processes transactions or tries to read transactions from that particular point in the circle. So you can have five jobs having the same hash value. It doesn't matter. It's not an issue. It's just what matters is the fact that these cron jobs are not going to be picking up different transactions. Like you have three cron jobs picking up one transaction at a time and trying to process it.
Yeah.
Yeah.
Thank you. So someone else's question is, how does this differ from, how does it differ from Google PubSub?
Okay, I don't know about Google Pops Up, so I'm not sure I can answer that question. But I guess I could. We can have a conversation about that later when I've read up on it.
All right, cool.
Yeah.
Thank you. Question. I see that the job is randomized using a hash, but how do you handle your P99 clients that tend to overload systems?
Can you come again, please?
I see
Trying
that
to
the job is randomized using a
okay.
hash, but how do you
Yeah.
handle your P99 clients that tend to overload systems? That's an
So
interesting question. But I would imagine that the hashing actually helps solve the overload problem, right?
Yeah, so like, yeah, it doesn't send as much as you want. It doesn't matter. So far, we've been able to have a hash value for that guy that's going to get picked up by another guy.
Mhm.
It's you can send as much as you want. Like overloading is not a problem.
Yeah. So we have maybe like 4 minutes to go. Someone said they struggle to understand the hash path. So can you explain it and possibly refer to maybe like some decent documentation?
Okay,
Um,
yeah. So I'll drop a documentation here. So okay, let me share my screen. Let me just
all
share
right.
my screen so I can do that quickly. Okay. Are you seeing my screen?
Yeah, 1 second.
Yeah, so this is it. So there's a concept called consistent hashing, right? Consistent hashing is typically used in, I'm just trying to explain how we came about this. Consistent hashing is basically used in say services that or server services that are used for caching, things like Redis, right? So what you want is you don't want it to be such that if a system goes down, you now have to basically change the position of everything that has been stored. If a system goes down, you want to add additional systems or additional servers. You don't have to change the position of everything that has already been stored in that system. You want to be able to just maybe move one or two message or one or two things that have been stored in that system without having to affect the entire system. So the concept of constant hashing is this. Look at let me not say the concept of constant hashing. How we implemented this into our system is this. Look at this circle. We have this circle here, right? In this circle, you can see that the circle is divided into three parts. We have 0 to 120, right? 120 to 240, or 240 to 360. It could be more than 360. It could be 720. It could be 1000. But for this particular scenario, I'm just going to use a circle because I think it helps explain things a lot better. So we have this guy 0 to 120, 120 to 240, and 240 to 0. Now these cron jobs are going to pick up things that any they are going to be is going to pick up transactions that fall within this particular segment of the circle, right?
Yeah.
And what happens is we are trying to compute a hash value for that particular transaction, and the
Mhm.
hash value is going to be between 0 and 360, obviously 0 and 359 actually, because we're using a modulo. So a modulo is like the remainder of that particular value. So we compute the hash code of this particular transaction initially. So say the hash code of this transaction is let me say 718, right? That's what we get as the hash code of this particular transaction, or minus 718. That's why you can see we have a math.apps here, or we
Mhm.
get minus 718. So what we need to do is we need to divide that by a hash upper bound, and our hash upper bound in this case is 360, right?
Mhm.
So dividing 718 by 360 is going sorry doing the modulo of 718 and 360 is going to give us I think that's 358, right? Because it gets into the 718 ones, and there's a remainder of 358. So that 358 is now the hash value for that particular transaction. And where is 358 going to be on this particular segment? It's going to be somewhere here. And because it is somewhere here, that particular transaction can get picked up by this cron job that falls within this particular segment. So that's how it works. Does that answer the
Yeah.
question?
Yes, it does. Thank you. I think we have one time for one more question. So remember the question I asked before about the request response cycle. So I guess the question, like, more clearly is, so when usually, like, if you put a transaction on Kafka, like a Kafka topic, it's
Yeah,
usually like because something has made a request somewhere. So a client has made a request, and because
yeah,
of that request, something has been put on Kafka.
yes.
So how does that client get the response back in your
How
system? So
how
like
does it?
how
Okay.
does the client get the response back? So say you want to initiate a settlement,
Yeah,
and because of that, you need to add a topic to Kafka. How does
yeah.
the client know that the settlement is complete?
Oh, so there's a point I mentioned where we have something in the transaction. That's the transaction body. We have like a job URL that is called. So that job URL is basically the initial client, right?
Mhm.
That produced the Kafka topic. So it just has an implementation somewhere for processing that certain transaction. The only thing is, at that point in time, it did not want to process that transaction. So it wanted to leave it on external system to call it to process the transaction when the
Mhm.
transaction was to be processed, right? So when the transaction service goes ahead and calls this particular URL, we call the service that's the initial client that made or that produced the message to Kafka. We call the service and we get a status for that particular transaction. So the service is already aware of the status of that transaction.
Yeah. So
Okay.
polling essentially. Yeah. Thank you. That clarifies. So I mean, we've come to the end of this. It's time for the next talk.
All right.
Thank you very much for your time.
Yeah, definitely.
There are a lot of questions that are unanswered. So if you can go to the main event, this is the backstage, but if you can go to the main event and go through the Q&A section of the stage, you would see
Okay.
like a bunch of questions from people. And if you could like take some time out to answer that, I think it's very, very helpful for them. Yeah. So thank you so much
All
for
right.
your time. Yeah.
Yeah, thank you too.
All right.
Have
Bye.
a nice day.